Okay, so we are going to solve this equation, the one-dimensional wave equation. Notice it's the very simplified version. I don't have a c squared there even. You're going to see what happens in the homework if there is a c squared and some other things. I'm going to go through solving the differential or solving the PDE this way. Actually, I think what you're going to be able to do is once we get the formula for this, without even going through this whole procedure again, you're going to be able to guess at what the form of the solution should be when there's a c squared there instead of a c. I think you should do that, but I think you should also go through the Fourier transform method just to make sure you sort of are reinforcing this Fourier transform stuff, just because it's one of the techniques we're using. It's one of the primary techniques we've used so far in this class, and it'll just sort of help solidify that. Okay, so here's what we're going to do. We have a double t derivative and the double x derivative. So if you think about it this way, if you think about fixing a point x and just looking at how that point moves up and down, if x is constant, we now have a second order equation in the t variable. And anytime you have a second order equation in the t variable, you need two initial conditions. You need to know the initial position and the initial velocity, that is the initial t derivative. So we're going to assume in this problem, we're going to assume that we know u of x0 is equal to f of x, and we're going to assume that we know the t derivative of u of x0 is equal to 0. In the next video, we're going to flip this. We're going to see what happens when this is 0 and this is some given function g of x. And then the solution to the whole problem where you have f of x there and g of x there is just going to be a sum of those two. Okay, so let's start this. Normal procedures that we're going to do. We're going to take the Fourier transform. So when I take the Fourier transform of the left-hand side, when I take the Fourier transform of the left-hand side, I'm going to get u hat, the double t derivative of u hat, evaluated at omega t, and on the right-hand side, it's just going to be minus omega squared times u hat of omega t. And now we want to solve this. So the characteristic polynomial, if you think back to ordinary differential equations, the characteristic polynomial is r plus omega squared. If we set that equal to 0, we get this. Omega is a real number, so omega squared is a positive number. So the equivalent form, r squared equals minus omega squared, tells us the roots are going to be imaginary. So the roots are going to be plus or minus I times omega. Now, in a typical ordinary differential equations class, the format of the solution would be a constant times cosine omega t plus a constant times b omega t. A constant times cosine omega t plus a constant times sine omega t. That would be how we express the general solution, because in an ODE class, we start with real valued things, and we want our answer to be real valued. We can do that here, but it's actually less complicated. It's actually more complicated to do that. It's less complicated to just say, all right, u of omega t, let's just do the normal formula here. It's going to be some constant, but it depends on omega, because as usual, we're only doing the differential equation in the t variable, e to the I omega t plus d of omega e to the minus I omega t. Okay, and you might be able to predict, if you've read the notes especially, that when we start doing inverse Fourier transforms, this is going to be a more convenient format to use rather than sines and cosines. Okay, so everything I've said so far works completely whether or not we're dealing with these initial conditions, or 0 there and g of x there, or f of x and g of x there. It doesn't matter. Everything up to here is normal, or is the same no matter what the initial conditions are. But now let's start bringing in the initial conditions. So when t is equal to 0, if t is equal to 0, this, as we've seen so far several times, this is just going to be the Fourier transform of the initial data. So f hat of omega, and if I, over here in my formula, if I plug in t equals 0, I'm going to get a of omega plus b of omega. Okay, that's good. And then 0, if I take the derivative of this and evaluate it when t is equal to 0, Okay, if I take the derivative of this with respect to t, it's going to be I omega times A omega. So I omega times A of omega, and then I said t equals 0, so that's just 1. And then over here, I'm going to get minus I omega B of omega. Okay, so what does this tell us? This equation here tells us A is equal to B. This equation tells us A plus B is equal to F. Therefore, A and B are both F of omega over 2. So what this tells us then is U hat of omega t is equal to F hat of omega times E F hat of omega over 2 e to the I omega t plus, actually I want to do it like this, 1 half F hat of omega e to the I omega t plus F hat of omega e to the minus I omega t. Okay, and now the solution is just going to be the inverse Fourier transform of this. And there's a number of ways to do this. For me, it's just most straightforward. You can use convolution, things like that if you want to. However you want to do it. Okay, there's several different ways to be able to do this. But for me, I think the best bet is just to do the inverse Fourier transform formula. Okay, so we're going to have 1 over the square root of 2 pi times the integral omega equals minus infinity to positive infinity F hat of omega e to the I omega t e to the I omega x. This e to the I omega t comes from that, and this comes from the Fourier transform formula, or the inverse formula. And then plus something similar over here. It's going to be plus the integral going from omega going from minus infinity to positive infinity of F hat of omega, and I'll get out of the way here in just a second, times e to the minus I omega t e to the I omega x dx, like this. Okay, now because I want the room down here below, I'm going to make some adjustments up here. I can combine this into one exponent, and it's going to be e to the I omega times t plus x. So it's going to be e to the I omega times t plus x. Similarly over here, actually to make things symmetric, instead of t plus x, I'm just going to write it as x plus t. Similarly over here, I can combine this into one exponent, but it's going to be x minus t. So it's e to the I omega x minus t. So e to the I omega x minus t. Okay, so what's happening here? Well, this is just the inverse Fourier transform of f hat, but evaluated at x plus t. In other words, this is f of x plus t. So this whole thing here is f of x plus t, and I forgot my 1 over the square root of 2 pi here, but this whole thing here is f of x minus t. And so what we have, the solution is going to be f of x plus t minus f of x minus t divided by 2. F of x plus t minus f of x minus t divided by 2. Okay, so we've done this Fourier transform thing to get to this solution here. But some of the assumptions that we have to make on f are going to be that it's absolutely integrable. But actually, notice what's going to be true here. I'm going to show that this satisfies the PDE with the initial condition. So I'm going to show that this satisfies the PDE with the initial condition, and then let's talk about that. So I'm going to erase all of this and just copy this. So u of xt u of xt is equal to f of x minus t plus f of x plus t divided by 2. So notice this is, if f of x is the initial profile, f of x minus t is that profile moving to the right at one unit of speed per unit of time, or sorry, 1 unit of distance per unit of time and just 1 unit of speed, and this is moving to the left at the same speed. Okay, so what this says is that if you start with an initial wave profile, it's going to break and move at 2 waves moving to plus and minus infinity. Okay, well, let's prove that it satisfies this equation. So if I take the, well, I need to show that the double t derivative is equal to the double x derivative. So I do the t derivative of u is going to be 1/2. Okay, if I do the t derivative of f of x minus t, using the chain rule, it's going to be minus, sorry, let me write it like this. It's going to be f prime of x minus t times the derivative of x minus t with respect to t. So that's going to be times minus 1. And then plus f prime of x plus t, again applying the chain rule to f prime of x plus t times the derivative of x plus t with respect to t, which is just 1. So that's the double t, or that's the t derivative. If I do the double t derivative, let me just make this change here. If I do the double t derivative of u, I'll have the 1/2. Now if I do the derivative of f prime with respect to t, or f prime of x minus t with respect to t, I'm going to get another derivative. I need to multiply x minus t, I need to multiply by the derivative of x minus t with respect to t, which is minus 1, so that just cancels and I get a 1. And then the derivative of this with respect to t is going to be f double prime times the derivative of x plus t with respect to t, which is just t. So this is the double t derivative. Okay, let's look at the double x derivative. The x derivative of u is going to be 1/2. Again, if I apply the chain rule, it's going to be f prime of x minus t times the derivative of x minus t with respect to x, which is just 1, plus f prime of x plus t times the derivative of x plus t with respect to x, which again is just 1. And then now if I do a second x derivative, that looks like a weird letter, or a non-letter, I guess. So if I do a double x derivative, okay, if I do the derivative of this with respect to x, it'll be double prime times the derivative of x minus t with respect to x, which is 1 again. And then similarly over here, it'll just be an f double prime, and again, multiplying by the derivative of x plus t with respect to x, which is just 1. Well, these two things are equal to each other. Okay, so it satisfies the PDE, and if you plug in t equals 0, you get f of x plus f of x over 2, which is equal to f of x. So notice something, this function satisfies the PDE and the boundary conditions. But what are the only assumptions that we needed to know about f? What are the only assumptions that we needed to know about f? We just needed to know that f was twice differentiable in the t variable and twice differentiable in the x variable. That is the only thing that we needed to know. So we only need to know that we have this function that is twice differentiable in both variables. That is the only thing that we needed to know. Now, those aren't exactly the assumptions that we think about when we have the Fourier transforms of functions. The way we are defining Fourier transforms, the function needs to be, absolutely integrable. But that's not what we're saying here. So this is a case of where the Fourier transform method, we sort of implicitly make other assumptions on f, but we get a formula and we realize that this formula works for less stringent assumptions on f here. And in fact, there are other ways of solving this equation that don't, require these bigger assumptions being made on f. But this is something very interesting to point out. In this equation, in the wave equation, notice what's happening. If f is just twice differentiable, the solution is going to be twice differentiable. This is different than what we saw in the diffusion equation. And I'll say more about this next week. But notice in the diffusion, or remember from the diffusion equation, our solutions were infinitely smooth, even if our initial data was not smooth at all. Even if our initial data was a Dirac delta function, our solutions were smooth for any positive value of t. This solution only has as much regularity, that is, as many derivatives and stuff like that, as the initial data, because this is the formula. So it's a completely different type of equation with solutions that satisfy completely different properties. But I'll say more about that next week.